Hey guys, welcome back to Vectors. Here we are going to consider vector addition, but in applications. So remember from the previous video, you should pick up the useful rules how to add vectors. If you have two vectors, you simply can use the triangle rule. So you set up the first vector like that, and to the end of the previous vector you attach the next vector. So actually it goes like head to tail, so head to the tail of the next one, and use displacement that actually connects the very starting point of the very first vector and the very end of the last vector here, and that becomes a triangle. So what about if you have several vectors in a row? So you set them up in the chain rule. So basically this is the general direction of how snakes, for example, moves and creeps. So actually this resultant vector is going to be from the very starting position of the very first vector and up to the ending position of the very last vector. So as you can see, this direction is against the general direction of this train or of the snake. Okay, so it goes in the opposite. Basically, is a general direction that way, so that's the opposite basically against, and that's your resultant vector. So here you can see a sort of polygon law or polygon rule, or basically head to tail for multiple vectors, for vectors more than two. Okay, so let's try to apply to the problems. So I picked them up from GCSE stuff and actually rearrange a little bit. Okay, so find the vectors which is equal to, and you're given different like setup for the vectors. So what do we have? We have a polygon, right? So we can see that AB is parallel to ED, so we've got those two vectors are parallel. Okay, and first we are going to find AB plus BC. So let's see, AB is here, so I marked the side, the direction basically. So AB is this vector, and then we've got BC, which is directed that way from B to C. Okay, so they already arranged in chain rule, so we're going to use the triangle rule. So we set up the vector that goes in the direction against the general chain, so it's opposite direction. So, or you just use the very starting point A and the very ending point for the last vector C, so you connect from A to C. That's your resultant. Okay, so the first answer is AC here. All right, let's move next. Before doing that, I just erased the results. Sorry, I need that. Okay, so CA, vector CA, it goes that way from C to A. Then AE is from A to A. Okay, they already in the chain rule. So in the last one, here and here, ED, it goes that way. All right, so we've got more than two vectors, so we cannot use triangle rule. So we'll use head to tail basically, or polygon. In this case, the vector which is going to be a resultant is, so starting in the very first point of the very first vector, C, and ends up in D, 1, 2, 3. Whereas the third vector, ED, ends up. All right, so that's the resultant vector. So we can say that the result is going to be CD, and this is direction of that vector. All right, so the last one, I erase all that, and we'll go to the last one. So DC is that one. We add up with BD. So BD, where are you at? So you're here, all right. It goes nicely. So vectors BD and DC already arranged in chain, and next we need to add BC. So BC moves backwards. So first I want to consider those two vectors, and what I'm going to do, I'm going to rearrange them. So I can say that we first going to have BD. Let's set up as the first vector. So during addition, we can swap them. You remember 3 plus 10, 2 plus 3 will give you the same result. So do the vectors. If you change the position and say, okay, that's the first one, that's the second, nothing will happen. So DC is here. All right, so that's the vector 2. What's the resultant vector here? Because BC goes in the way BC, it goes in the way back. So that's why first ideal is to find the interim result for BD and DC together. So BD and DC actually vector BC as a result, okay? So that's the resultant vector, it's here. So we've got the result, and on top of that, we need to add BC as the third vector. So actually, what we have BC plus BC. So it means we can set up the chain rule, but it's obvious clear that on top of that, if we add the same vector BC, BC will get double BC, right? And that's a very interesting feature because we've got a new vector 2 times more than the original one, okay? So we've got 2BC for addition to identical vectors. If we add them 3 times in a row, we'll get 3BC, all right? So we actually discovered new property and features for the vector, which are collinear. Collinear vectors, they lay on one line or on parallel lines. They might have the same direction, they may have different direction, and in this case, they're actually equal. If we add up 2 equal vectors, we get 1 with a factor of 2, okay? That's what actually we have. So BC and with BC, actually we just do double lines, but we don't change direction. So that's the result. Okay, so we've got all 3. Let's move next. Hope it's clear. So that's the word problem. So let's try to consider. So here is the swimmer. He can swim at 5 kilometers in calm water. So you understand that if the swimmer goes somewhere and swims in the river, whereas there is drift or flow, right? River flow, obviously their 5 kilometers per hour will be changed according to the river directions. So actually, if direction is the same as the swimmer goes, you need to add velocity because obviously the speed is going to be more as a resultant. But actually here we are going to prove using addition for vectors. So we have the swimmer, velocity in calm water is 5 kilometers per hour. He decided to swim in a river where the current is 1 kilometer per hour in a westerly direction. So the key values here is 1 kilometer is the velocity of the river and towards western or to the west. So we can consider that if we have this as the river and we set up west direction that way, so we can set up, let's say this one cell is 1 km per hour. So we use the scale. So one basically cell, or let's say 0.5 centimeters, if we consider it as one cell as 0.5 centimeters correspond to 1 kilometer per hour. So we use the scale. Remember in the very first video about vectors, I mentioned the scales. If you want to depict that, you need to use the proper scale. And let's say that 1 kilometer per hour is simply 0.5 centimeter, or just simply just one cell on the draft. Okay, so on the map. And we have first the swimmer swims with the current. So it means we set up swimmer, and it's here, and vector corresponding to 5 km per hour. So we need to count 5 cells, right? So 1, 2, 3, 4, 5. That's the vector for the swimmer velocity, which is 5 km per hour. So that's the river flow, and that's a swimmer, okay? So we set up and we can mark with indices like swimmer velocity, and the river stays for river flow. Okay, so in this case, what we're going to do in order to define the resultant velocity of if he swims in the same direction with the current. So actually what we're going to do, the resultant velocity in this case, resultant is actually river plus the swimmer. It's obviously, right? How you can check. So if you put velocity of the swimmer actually equals to 0, it means that river flow will carry the swimmer to the west with 1 km per hour. If he swims, or relative to the river, it swims with still 5, but relative to the shore, right? To the shore, to the observer that stays on the shore somewhere here, that's the shore. Actually, the observer can see the swimmer moving faster. And actually, 5 plus 1 km. So if we need to depict the resultant vector, is going to take 6 cells in a row. So the resultant vector is simply 3 and 1 was 3. So it's here. That's the resultant vector for the case A. A total or resultant velocity, which is 6 km per hour. Okay, so let's go next. If he swims against the current, obviously you understand that in this case, what are you gonna do? So how to do it, like basically you need to use resultant vector and you need to swap direction for the swimmer the way back. Now it swims the way back, so actually I tried to eliminate that and say, okay, now the swimmer in the river turns velocity back, so from the end of the river vector it swims backwards for the length of 5, so that's 5 km per hour, the swimmer. In this case, if we add them, so where's the vector that connects the starting point of the first vector, in this case that one, and the ending point of the swimmer vector? It's here, so I just put dot line. So let's see, that's starting point of the river, of velocity of the river, and the ending point here. So actually this is flat case, not any shape arranged here, but anyway we stick to the rule and we say, okay, that's gonna be the resultant vector. So this is the resultant vector, and you see in cells is gonna be 4. So resultant vector is going to be 4 km per hour. But you know, sometimes it's quite complicated. So actually, in the vector way, we need still to add them. We're not going to subtract, but because directions are opposite, so actually that's the same as we subtract from the greatest value of vector, we subtract the lowest value of another vector. And that's how it works. And we've got to 4, okay? So, or you can build up according to the rule. If you want to prove using a head to tail rule, just simply again start at the very start point of the first vector, V, right? V river, this one, and you end up in the end of the second vector, which is 5, and you arrange them so that actually it works in that way. Okay, so the starting point here and ending point here, and dotted line represents the resultant vector. You can see it 4 cells in a row. But technically you can subtract if you cope with values. Okay, so next one, to the north, across the river. Okay, so he swims to the north across the river. All right, in this case, we can understand in a different way the problem. So look, he's gone, let's assume that's the river, and now he swims to the north. So what we can say? We can say that he swims in calm water to the north with a length of 5. Okay, I just enlarge a little bit. Okay, so the river still flows to the west with 1 km per hour. That's the river. And what about the swimmer? He starts, let's say, at this point and goes to the north. If it's in calm water, actually he still be moving to the north. But what if it's a river? So what will happen? What's going to be the actual direction in this case? So you just simply need to add vectors as normally we do. So for the swimmer, we need to add river vector, and that's going to be a resultant. So a resultant vector of the velocity. So we set up another vector, which is 1 km, that's for river, and this is 5 km for the swimmer. And again, according to the rule, what we're going to do, we are going to connect the very starting point and the very ending point. So it goes that way, actually. So this is going to be the velocity, okay, of the resultant velocity of the swimmer. So that's the vector. How to find, because the vector need to have magnitude, and actually direction. Here's the right time to see that. So actually what we arrange a triangle with one leg to be 1 and this leg to be 5, right? 5 cells in a row. And hypotenuse becomes the resultant vector here. Okay, that's hypotenuse. As the vector goes that way because of the rule, and we need to find the length of this vector. So let's take up and see what's the length for the resultant vector. Okay, so in order to do that, we arrange a right angle triangle. Okay, we've got the right angle triangle here because direction of the river flow perpendicular to the north direction for the swimmer, and we want to calculate. Okay, we want to calculate height. In this case, resultant is height, and we take the square root of 1 squared plus, so the second one is 5 squared. Okay, so the resultant vector will have the length square root of 26, or if you calculate using calculator, just do that. Take the square root of 26. Okay, it's going to be 5099, or simply to 2 decimal place, the magnitude for resultant vector is going to be 5.10 to 2 dp. Okay, so that's the value. But what about direction? In order to find direction, we need to say, okay, we need to say that we need to establish some angle. If we use the bearings, so, and we've got that vector as the resultant, so from north direction in clockwise, this is going to be the angle. But okay, we can find this angle theta, right? And we can find the bearings actually from the north direction, so bearings. Okay, so let's try to do. So first we're going to calculate this angle, which is, let's say, theta. So what we can do, just remember trigonometry. So angle theta can be determined through the ratios for tangent, because we've got two legs, 1 and 5, so we can arrange the ratio for tangents. So tangent theta, by definition, is going to be opposite side, right, to adjacent. Okay, in our case, opposite is which is opposed to the angle, so it's 1 to 5. That's going to be the angle theta. Okay, and basically the variance is going to be 360 minus theta, due to this angle is basically 360 degrees. So that's why, first of all, let's try to find theta itself in degrees. So we use 10 minus 1, as you remember from trigonometry. So 10 minus 1 of 1 over 5. So you will use inverse tangent. It's in the second row if you're using smartphones, calculators. So 10 minus 1 of 1 over 5, or 0.2, right? As decimal. So it's going to be 11 and 31 degrees to 2 decimal places. So 10 minus 1 gives you that value. Alright, so in order to find the variance from nose direction, you simply need to subtract that from 360. So you take in 360 and you subtract those 11 something. Okay, so the variance is going to be 348 and 69 degrees. Okay, that's the variance. Alright, so look guys, what's the nuance for this problem? The nuance is that we understand that in calm water it goes to north direction, but due to the river flow it's shifted a little bit, so that the actual direction is not actually north. If we understand in this case, that's the solution. But what if the actual direction perpendicular to the shores? So actually the swimmer, due to river flow, goes to the north. So what actually happens? Look, what actually happens? So that's the first case. But the second case, if we understand that this is the river, and so the actual direction is from here to the north. Let's say 5, 1, 2. So it's from here to the north. And this is a resultant. Let's say this is a resultant velocity. Okay? This is the vector of resultant. But how it can be arranged? It can be arranged using the following judgment. So it goes up. If we set up the river, yes, so let's say a river goes that way, so the actual speed or velocity of the swimmer is going to be more than the resultant. So this is 5 and now this is 1. So why is that? Because resultant velocity in this case, it's v swimmer plus v river. Hence we've got still additions, vs plus vr. However, in this case, we understand that the resultant velocity is going to be lower than the velocity in calm water, because some part of energy actually goes into resistance to against the river flow, and that's why the swimmer works against the force that actually carries the swimmer to the left hand side. So in this case, how to calculate the resultant? It's one leg, while we have height here and another leg 1 here. So we can set up Pythagoras again, right, in order to calculate one leg. So we can set up 5 squared, this is height, equals to v resultant squared plus 1 squared. and from where we can figure out the length for the resultant vector. So it's going to be 26 minus 1, which is, 25 minus 1, which is 24. And we need to take square root. Okay, that's the value. If you calculate, you'll see that the value obviously less than 5 because half is the longest side. And it's 5. So let's take square root of 24. And it's going to be 4.899, or simply to decimal place, we've got 490. Okay, it's a little less, not so much, but a little bit less than the speed of income water, so due to the effect of the drift. And if we want to find the angle, now we want to find the angle, actually, that's the bearings. In this case, we need to say that how to find the angle of the bearings. So let's say theta. So theta, in this case, we are given hypotenuse, we're given the opposite side, so we'll use sine, right? So remember, the opposite side is always hyp times sine of theta. From where sine theta is actually, so opposite side is 1, hypotenuse is 5, so it's gonna be opposite to hyp, or simply 1 to 5. And actually it's correct because the sine should be less than 1. So tangent doesn't need necessarily to be less than 1. Okay, but in this case it's correct. So that was our check. And now we're just going to use again inverse function for theta, sine minus 1 from the value 105. Let's go to calculator. So second row of operation, sine minus 1 of 0.2, it's 105. And we've got 11.54 degrees to decimal place. You see the result actually different, and you understand why, because actually we've got different triangles. In this case, triangle has the leg of 5, right? And another leg is 1, so hypotenuse is more than 5. While here, the longest side is 5, so the other leg is 1, so this leg is going to be less than 5. So we've got different triangles. They are actually pretty close to each other because the angles are really close. The difference is in 1 in the first digit after the decimal point. However, the problem in this case is understood as the swimmer. Actually, the real direction is to the north, right? So that's why the actual speed or actual velocity of the swimmer need to be directed a little bit to the right, so sort of northeast direction, closely towards the north, of course, but due to the effect of the river. And we arrange the addition rule in the right way. Okay, so that's details actually that very significant. In case you are not you're not sure, so make some comments about if you're sitting exam and trying to solve. So making some comments or ask the teacher to clarify, is the actual direction to the north, or actually it's in calm water, so that you need to take the effect of the river on top of that. Okay, that's the details. Come to the teachers in your class, probably clarify these details. They're very significant. Don't be scared. Try to give them questions in order to understand with them. So in order don't have any so sort of uncertainty and this sort of problems. Okay, so I hope you like that. I hope you have a deep understanding now how we can apply. We've got several sort of different problems that we're going to discuss in the next video. Thank you guys. Don't forget to subscribe, share these ideas to anyone who is interested in math. You're Daniel Dallas. See you later.